Uh, so homework 0 is graded. We just want to, I'm just having the TFs, I want them to chat a little bit about some of the differences between them, just to make sure everything's roughly normalized. So those will go out today or tomorrow. Peer review assignments, I think, are almost ready as well. So those will also go out, and homework 2 will also come out. So it'll just be a flood of email from us. Who has not tried the Cython installation check? Oh, please do soon. All right, just so that if you have and it's working, if it gets through all the steps and prints out AVX, great. There's still, please give feedback. Anything that goes wrong, let us know on any system. We want to solve it because each system we do solve. Don't worry about, warnings are generally not a problem. It's just the compiler does tend to complain about NumPy, about unused functions. Those are okay. If it goes through all the code, it's okay. So don't worry too much about warnings. If you want to post them and ask about them, that's fine. Just post on Piazza and we'll make sure that they're okay. But especially like unused functions, the Cython to C translator produces a lot of functions that aren't necessarily needed. NumPy has a bunch as well. So warnings are generally not a problem if it goes through everything. OSX in particular, I want to talk just a little bit about it because most of you are on OSX, and it's good for you to know the space of what's going on there. So my thought was we'll just use Clang because Clang is the default on OSX. Even when you call GCC on an OSX system, unless you've installed Homebrew, you're not actually getting GCC, you're getting an alias that just runs Clang in GCC mode. And this has been Apple's been shipping Clang as its compiler or the LLVM underneath for I don't know how long. But OpenMP was only added earlier this year. And my thought, I had hoped that installing Clang OMP with Homebrew would be a nice, it's all Clang, so everything would work better, but that's not really happening necessarily. Some people have run into problems with that. We'll keep working on that. If you're adventurous, you could probably switch. There's that setcompiler.py file, and if you have GCC installed with Homebrew and you're happy with that, GCC has had OpenMP support a lot longer, and you could probably just bang on that setcompiler file to make it use GCC instead if you have that, and if you're brave. But do give us feedback. Homework 2 is going to depend on this. I'm going to integrate the changes that we've made and what I've learned from the Cython test install into the Homework 2 setup so that it hopefully just works. There is part of it that uses AVX. AVX is basically 8-way parallelism in a single instruction for floating point operations. We're going to have some of it in Homework 2. I'm going to talk about it on Friday. Give you an intro to how it works, why it's there, how to, what the instructions are that are available, sort of the basic ones, enough to get you oriented and enough that you can do part of the homework with it. If you don't have AVX, which only really came out last year, we've actually got an emulation header that's in there that turns into SSE, which is sort of the previous generation, which does 4-way parallelism, but we can emulate the 8-way pretty well. Again, more testing. If the Cython install check works for you, and prints out the AVX results, it doesn't hang there or crash there, then you're probably good, okay? You should retest. So have you tested again since I added the header? Okay, well I replied to you on Piazza asking you to do that, and so we'll see. So that may fix it for you, because I know your machine doesn't have AVX. All right, when you do peer reviews, and for homework 1, and in the future as well, there tended to be a lot of commits in this last homework, which is good, right? You should do a little bit of work, get it working, commit, do a little bit of work, break it, commit, fix that, commit. It's very hard to do the comments on the files if you go into the commits tab here on the peer review. We'll send you a link to this page, which is files changed, which basically takes all the commits and puts them in one big diff. So that really all you're looking at are the contents of the file at the last point of the commit. You can still comment line by line and whatever. Just make sure it's there, because if you try to do it in the commits themselves, it's going to have all kinds of historical changes that may or may not be valid. So just make sure when you get the peer reviews that you're committing on that last tab, the file's changed. It'll be the cleanest one, so it'll be obvious, I think, if you drift off of it. All right, I think that's all for this. All right, the rest of the time I really want to just talk about this. There's been a lot of good discussion on Piazza. A lot of pushback about, I mean, if you just read the paper, if you just read the abstract, you might think, okay, well, I'm not going to use Spark, right? I'm going to do all my problems on a single machine and possibly in a single thread for simplicity and speed. But there's been a lot of pushback about what actually is good and bad about Spark and other cluster systems. So one of the questions that's sort of coming into this, right, Spark, MapReduce, any of these is, what do you use them for? Big data, what's that? Anyone?
It's not gigabytes data.
Not gigabytes. Why not?
Because like it was testing on gigabytes of data.
Well, that's a single case. I mean, in general, would you say something gigabytes is big data? No, not generally. Probably not, because gigabytes, if it's gigabytes of data, it fits in your laptop's memory, right? It's in most laptops' memory, not all. Up to maybe even 10 gigabytes, right, before you're gonna have to start going to disk, or even if you do. There are a lot of out-of-core algorithms that can run on hundreds of gigabytes, just if they're single pass, right? So you load everything from the disk, deal with it once and be done. Not big data. If it fits in if it's an out-of-core algorithm that doesn't require going to the disk more than once, you load it on your laptop or on a thumb drive or something and go. So okay, bigger than gigabytes. So when would you definitely need to use Spark?
More than 3 terabytes.
More than 3 terabytes. That's a good answer. Well, it depends what you're doing with it. So more than 3 terabytes, yeah, probably. Terabytes of it is a bit much to deal with on a single machine.
I think a good general rule is if it doesn't fit on your computer, you probably don't use it.
Yeah, so if it doesn't fit on your computer, you might get access to a cluster with a bigger computer, right? Or you might get put in a grant for a very large RAM system, right? Other cases. There was a very good one posted on Piazza about, I'm gonna make a new Spotify. I don't know I forget who posted it, right? I'm going to create the next Spotify. If I run it on my laptop, and I'm gonna build it on my laptop, and it's gonna be super cool, and then I'm gonna start serving it to my friends, it's gonna become super popular, and then what's gonna happen? All right, it's gonna crash. I'm gonna close my laptop. You need something like Spark, or at least something in the cloud support, multiple systems. When you're dealing with resilience or heavy bandwidth, or very highly fluctuating bandwidth, right? Your laptop might be able to serve 100 users, but then it suddenly spikes up to 10,000. You can't grow that easily, right? You need to go and buy more laptops. Part of this is, how do you measure costs, right? What's the cost of using Spark? Blood, right? That was basically my impression. Right, what is the cost of using Spark?
Your efficiency per core is terrible.
Efficiency per core is terrible. Good. I/O. Yeah. So the communication cost, right, between nodes. So and we talked about this. This is something we tried to optimize for, right, with the shuffle cost. That is where we considered all the costs to be in Spark. And so these two are tied together. The efficiency per core is poor, especially if you're spending a lot of time dealing with communication, or talking between machines. So you try to make that efficient. There's another reason that in almost everything we did, all the examples we showed, everything in the homework, why was the efficiency per core particularly slow? Not particularly slow, but also even slower. What were we writing in? Python. We interpreted Python the whole way, right? So even when we were not communicating, we had that other slide when we were talking about efficiency of Python. When you choose to do something in Python, you're choosing to do it slow. That efficiency is not your key point.
Also my point, like, he uses it on his machine. I'm using Rust, and I have like a shitty machine
20 times kind of, I mean, with Python, it depends. So when you say Python, do you mean pure, in interpreted Python? Yeah, that's not gonna go so fast, especially if you choose to represent your graph in lists or in a dictionary, yeah? If you choose, what? Or sets, yeah, any of these. All of these are poor choices, right? If you've got, so Python is not the right choice when your data is pure Python, is not the right choice, or any interpreted languages is not the right choice. MATLAB's probably okay because you're forced to use a matrix there, right? But you could use cells and make it slow.
Was the bottleneck with Spark really the interpreted Python you wrote? I felt like the bottleneck was, the shuffles and
So was the bottleneck the slow Python? No, it was not the bottleneck in general. It's this, yeah, so you can see this when you do something like count or the filters. How fast did those run? Now, still, they're not. So when you translate it to Rust, or you write it in Python, or C, or any compiled language, you're gonna get some speed up, and that speed up will probably be around a factor of 10, give or take, depending on what you're doing. It could be much higher, right? The matrix multiply example from Charles Iserson's thing, went from whatever, 48 hours down to 2 seconds, 5 seconds, something like that. But that was representing a big matrix as a nested lists. So this is very slow. So no, the Python was not super slow, but it was probably a factor of 10, possibly, depending on what we were doing. You can process data, in interpreted Python, if you're processing data, even just doing string splits and things like this, can be quite slow. That's fine, it's very flexible. If you were to optimize for the computations we were doing, then you could probably get a factor of 10 improvement through compiled code. But that is not, I mean, if you look at how long it takes to do a flat map and then a count or something like that, right? It's very fast, right? This is not the limit. Partially because it's split across, at that point, those things are worker side only computations. So no communication, so pretty fast. Was there another comment over here? What are the benefits of Spark though? Right, why is Spark still worthwhile? People still use it, real companies still use it. So I mean, that could just be the wisdom of crowds, right? Crowds are super wise. That's why they're called mobs. Is it just everyone's doing it? It's very good. So the resilience, right? Spark has built-in, and you can configure it even on large clusters so that if you get resilience because everything knows its history, and so if there's a failure, which will happen on a very large data set, almost surely, right? When one computer dies, goes offline, or is taken for some other point, you can just recompute from where you were. Or rebuild just that piece of data, go on computing, right? You don't lose work. That's particularly important when you get to really large clusters, right? You need some sort of resilience. Google, for example, they have, I don't even know, some large percentage actually of disk drives are bought by them and a few other companies. When a computer fails in Google land, do you know what they do? Just turn it off remotely. They just leave it, right? Computer dies, whatever, new computer. They're bringing on so much that it's actually just easier just to wait until everything dies, and then eventually they'll go in and upgrade everything, right? They won't even go and try and fix any individual machines. It's much easier, much cheaper just to ignore dead computers or even misbehaving a little bit. So what's the benefit of Spark though? What are the other benefits? Would you want to hand code PageRank on the entire web? Basically, I just give you a bunch of computers and no infrastructure except for Ethernet cables and Python, right? Say, go, PageRank, please. Here's the data. Is that gonna be fun? No. As someone said on Piazza, Spark is a high-level tool. You're gonna pay a price for that, right? So the benefit is it's very easy to solve problems, right? PageRank is very easy to write. It's 10, 20 pages long. 20 lines long, right? And you can scale that up to whatever size data set you need to, okay? Other benefits of clusters versus single computers. Latency is high, but what increases as you add more computers. Scheduling overhead, yeah, it tends to grow, the scheduler doesn't grow too much. So this is the bad thing. What's a good thing that grows, though? What do we get for multiple computers? More disk space, throughput. This is another good, yeah, more disk space, so this allows us to store a lot more. Throughput, right? So we have 10 petabytes of web scrape data that we want to analyze. We split it across hundreds of machines. Now we have just a few terabytes, tens of terabytes each. And we can read that at the same time it costs to read 10 terabytes instead of the time it costs to read single petabytes. So we get this huge bandwidth increase, basically linear with the number of computers. We also get much more, if we start farming out queries, for example, in Spark to individual machines, they can be handled by, if we just have a task that needs taken care of, we can put it on any machine, right? So we can get this very low latency response to queries or in events. Yeah, so there's bandwidth within. Yeah, so you're talking about, so the question is, what sort of bandwidth do I mean when we get a bandwidth increase? So we don't necessarily get a bandwidth increase between computers, right? A talking to B. We get a bandwidth increase in terms of we suddenly have, if we think of whatever storage we have underneath as just a big disk drive, but it's spread across all these machines, like Hadoop, the Hadoop file system does. When we load a file, if it's very large, right, if we load it through one computer, it's order n, whatever. If we load a large file and are distributing it to workers, compute. But when we spread it out, each disk drive reads independently on a separate machine. So that's the bandwidth I'm talking about. Also the bandwidth to external networks or things like this. Queries can come in and be farmed out to any sort of server, sub-server. And so we get a higher bandwidth to our local drive, our local memory, as long as we've distributed the data, as well as to external services as well, or external sources of data or inputs or things like this. Does that explain? Okay. So which cost do you measure, right? This also came up in the Y Combinator discussion, some of it on Piazza. What do you look at when you're trying to optimize a problem? What's the most obvious one? We've got a large problem. Well, how do we tell if we're doing a good job of making it faster? Time. Now, how long does it take? How does that scale? How does that scale as we increase processors, right? How close are we to optimal, basically perfect scaling? So one thing, time versus processors. And this is where the sort of the cost paper was like, Spark is not scaling, or many of these things are not scaling very well. But as many of you pointed out, was that a fair, do you feel like that was a fair comparison in this paper? Yes? Hands? Yes, it was a fair comparison? No? Okay, why not? Somebody raise the hand, come on. The data is relatively small. Yeah, and well, they did do a little bit of scaling analysis in the paper, right? They showed two versions of an algorithm, one of which scaled very well, right? One of which scaled very poorly. They showed the scaling, sort of, the improvement over serial of the same, two algorithms as you increase processors. But when they showed actual compute times, right, it didn't matter. The constant was so small in front of this poorly scaling algorithm that it didn't matter. So you need to measure not just scaling, speed up, but there was that great quote, you can have another computer after you show that you can use this one. Right? You can have another core even after you show that you can be efficient here. This class is not so much about optimizing for single core, but it is important. Right? If your single core algorithm, if you could just write something very simple and do a very good job, it's going to be very hard to get very good scaling beyond that. Just because As soon as you add, well, if you add another core, maybe you can get scaling. That's what homework 2 is going to be about. How do you improve performance when everything is very fast? But as soon as you take and create another computer, right, that's, what is it, 1,000 times farther away than memory? Something like this. I forget the number. It's about 1,000 times faster, even if it's right next to it. And so anything you have to do that's between those two computers, you've suddenly taken a huge hit in latency. Right? So at that point, you better need that second computer. Or it needs to be something that's got a very low amount of computation. How do you tell when it's not working? Does this make sense? How do you tell when you need to switch? Opinions? What? If it's too slow. How do you say when it's too slow? Experience? That's a good answer. I don't know yet. Someday I might. Out of memory. So that's certainly an approach that, then you need to think, why, so out of memory errors. In the cluster domain, how do you fix that? More memory, right? More machines. You're going to add to it. What's going to go up? Communication. So you're going to start trading off, can I store it versus can I compute? What's another approach? More tasks. That's a very good answer. Though more tasks, so you're talking about basically, more partitions, right? No, it's fine. They're interchangeable in the Spark world. Is that the same? So more tasks might save you from memory errors, right? Because it's going to be able to swap out one partition and work on a new one. It's going to be slower than just adding another machine, right? In general. Because you're still going to have all this communication, and now you split RDBs. And a lot of the communication may be inside, but the cross-partition, or the cross-machine communication is still going to be the same. But that's also a good idea. But in general, on a cluster, you're going to just, well, I don't have enough memory to store this, so I'll just get more memory by adding more machines. There's another answer over here. How else do you know when it's not working? It's too slow. So the answer was if you double the size of your problem and you see very poor scaling, basically. If your approach doesn't scale. So under the Gustafson-Barsas model, right? So you double the size of your problem and you double the size of your compute and you don't see anywhere near the performance, then maybe you have a quadratic algorithm, or some nonlinearity in communication. This is a very good example, right? I'm going to double everything and see if I get the same speed output. Other ideas, other things that go wrong. What goes wrong, So let's see. What are things that we can't necessarily do on a single core besides just if it doesn't fit? Are there other examples of this? Right, so if you don't have resilience, so you're going to be forced into a multiple machine model just so that you can have high uptime and responsiveness. Then this is a very good time to make sure your approach is working, right? It's very easy to understand if you have a single machine handling all your queries, you know how it scales. It probably drops off roughly linearly as the number of queries increase. If you have twice as many queries and you have twice as many machines, do you still see that speed improvement? So this again comes back to force it into the Gustafson-Barsas model and see how it does. And if it doesn't do well, you need to consider why. What guidance can we use? This is a bunch of ideas. What can we sort of use? So some typical problems that we might do. PageRank on the web graph. Where are you going to do this? Which model are you going to use? WebGraph's big. It's really big. Yeah, I forget what you're going to do this in Spark. You have to do this in MapReduce or Spark or Google Data, Shove It or whatever it's called, Data something. You have to do this on multiple computers.
If I'm not
Where's the Scala expert? He's not here. I think Scala, what? Yeah, possibly. Scala, I think, does just-in-time compiling and is also, I think, does very strong type inference, and so I believe it would be faster. I mean, so it's not that Python is intractably slow. It's that the compute portion in Spark, if you're running in Python, is going to be about 10 times slower, possibly, the compute portion. But you still have all the serialization, fetching from storage, writing to storage, and then the huge thing is shuffles, right? So it wasn't intractably slow because we could do things like split lines into words, right? And that was, you know, there was time, but it was comparably very little time. Even though it was running in interpreted Python. So it's not that it's intractably slow, it's that when you see this improvement in single core performance, some of that's coming from compute, a lot of that's coming from reducing the communication cost. Much more of it probably, and serialization and all these things that land there in Spark. Okay. Python's just fine for a lot of this. Like you can process very large files, text files in Python. It's just if you need to process them fast, you need to be in Python or C or something compiled, okay? I forget what, so PageRank, something that's super large, you're gonna put it on clusters. How are you gonna make it faster? You're gonna try to reduce machine-to-machine communication. A lot of you I've talked to about this example. I don't know if I mentioned it in class. Do you know what Google does? I mean, they basically have something that's distributed data with hashes and things, you know, same sort of framework as Spark. Do you know how they optimize PageRank for minimal communication? I've talked to you a few about this trick. So you can set your own partitioner function, right, in Spark, and you can do it in most other things. Google partitions not by the URL or the node name or node number. They partition by the node domain. Why? Ideas? Why? Sorry. Web pages in one domain are more likely to link to each other. Very much higher, right? You go to a CNN page, most of the links, possibly all of the links, are to another CNN page. You're not going to have half their links to Fox News or something like this, right? Most sites link to themselves, you know? Most people think about themselves most of the time, and then they blog about it. So if you partition by domain, all of the, you know, you're pushing weights around in PageRank. You're just saying, I take my weight, my importance, and I give it to all my neighbors, and I receive importance from them. If most of your neighbors are in your own domain and you partition by your own domain, then the only communication between partitions, the only shuffle costs are cross-link or cross-domain links, which are much smaller. So that's a sort of classic, not classic, I mean, I guess it is by now. That's the trick for PageRank to remove cost. You can figure out other partition strategies based on your graph structure. That's something where you need to be problem domain specific, right? You have to understand what is the data that I'm analyzing, why does it matter this way? All right, what model are we gonna use for image processing? We did use Spark for Mandelbrot, that was not perhaps optimal, but.
So is it acting up to the Hilbert curve?
So that was very interesting, and we might want to talk about that some more later, actually. The Hilbert curve that came up in the cost paper, this idea of, well, if I have a graph, and I want to pass information around, if there's no correlation between, this didn't make a lot of sense to me, right? He said, we'll organize things by the Hilbert curve. Let's just save that. I'll talk about the Hilbert curve because it's interesting. It's a nice way to partition memory or order basically 2D objects so that they're coherent spatially. But let's save that for maybe next lecture. It is a similar idea, you know, partition my graph using some spatial layout pattern. All right, image processing. Am I going to use Spark for, you know, I do image processing. I process petabyte data sets, or I try to. Am I going to try to process individual images by splitting them across Spark? No. What am I going to do? All right, images are not huge, just by definition. Even really large images are not huge. They're not big data. And generally, when you're processing images, you're not processing a lot of images. I'm going to keep it on a single machine, right? I might keep it on multiple single machines, but it's still going to be individual machines. Sequence alignment. Do people know what sequence alignment is? So sequence alignment is a biological problem where you've read out, for example, 2 genomes, and you want to find how they match. You've got some function that basically computes how they match. Genome's about 3 billion base pairs, 3 million base pairs. Not a lot of base pairs, million, billion, these are small. Single machine usually, but what if I've got a lot of genomes and I want to align a new genome to one of them? Spark, cluster, something simple, right? It's an embarrassingly parallel problem. But usually single machine. Web services, we already talked about this. Resilience becomes key, and then you need multiple machines. Other problems, matrix multiply. How big? Right. GPU is awesome at this. We'll talk about GPU. GPU is also really good for image processing. So most of this is, where does your problem map? Is it embarrassingly parallel? Are there few communication costs between pieces of data? Can I do some sort of trick that limits the communication cost based on what the data is? Okay.
Why was there no mention of threading or multiprocessing? Is it just because it's a cost problem?
Partly because, okay, so partly because it's harder to optimize this. It's harder to do, for example, union find or PageRank. Actually, PageRank's not too bad to do multiprocessing. I think it was partly just, if I do that, it gets more complicated, right? He wanted to show, I can write something very simple. And people were talking about how optimized his code was. It wasn't that optimized until he started doing like the Hilbert curve. Even before that, the performance was very good. Partly because of complexity, right? His argument was, their argument was, it was a few authors. Their argument was, you can write fairly simple code that anyone who could probably write Spark could probably also write code very similar to this and get very good performance comparatively, right? So, I mean, a much fairer test would be I took someone who only knew Spark and had them write it in single thread and had them, I gave them some basic tools on the level of Spark and had them do this. So it was partly just the argument is stronger and partly it's simplicity. It's not that hard to take advantage of multiprocessor systems for some of these algorithms. It's a little tricky. That's partly what the leaderboard challenge that I put out there, but no one's entered yet because you've all been busy with other things. But it's possible. It's possible. Other questions or comments on the cost paper before we leave it? No? Okay. How many people think they would still use Spark? How many people would never use Spark again? That's fine. How many people would never use clusters? All right, good. All right, I want to do, with the remaining time, just a little bit of threads and locks review, particularly if you have any questions. Just on a high level, Python threading is a high level useful for I/O bound tasks. You can use it for compute as well. And we did some of that. We showed some examples. OpenMP threading is more low level, a little more efficient, or more efficient in general, and has fewer structures. Doesn't have things like events and some other things that you probably saw. The other part of the reading, which didn't get as much attention, but rightly so, was the multiprocessing, or the threading module. You have things like condition variables and semaphores and things like that. Those don't exist in OpenMP. You only have locks. And then this fork join model. Homework 2 will focus more on OpenMP threading. There won't be really any Python threads. Okay? Are there questions about Python versus OpenMP threading or threading locks at all?
At the very end of threading, so first, like, what's the difference between the semaphore, the condition variable, and the log, and the
Okay.
logs?
So what is so maybe I should have an actual, these are all terms from Java threading and such, so maybe I'll do a lecture on those probably at the end of the semester because you don't need to know it yet. But what is the difference between locks, reentrant locks, so reentrant locks, semaphores, condition variables, and events? I think are those sort of 5.
Yeah, events, yeah, I don't know.
So locks and reentrant locks actually both exist in OpenMP. It's called a nested lock in OpenMP. And a nested lock is something where the same thread can reacquire it, and it just increases a count.
And then he has the priority on it?
It doesn't have a priority. Priority is another thing. That's operating systems. So reentrant locks, you can reacquire, and that's very useful if you've got, for example, a recursive function where you don't want to check if you're already one level in and already have the lock. You just reacquire the lock. So if you lock a tree and then you want to parse a subtree and the first thing to do is to lock that tree again, you can use a reentrant lock. That keeps all the other threads out but allows one thread to keep reacquiring with the same code. So the semaphores, events, and condition variables are just higher level communication structures. We'll talk about them later, I think. It's not critical to know now. You can read through it. They're useful in some cases where you don't want to busy wait. So you can always emulate them using a lock where you try to acquire the lock, and if you fail, you sleep for a little while and then go back. And you just sit and spin. That's called a busy wait loop. You just keep trying to reacquire the lock. It's inefficient, right? You should be giving up and waiting for a signal when the lock is ready. And that's where these semaphores and events come from. Basically, you can sleep, just give up processor time until such a time as someone says, wake up. And that's all that it is. But OpenMP doesn't have them, so I don't want to, we're not going to use them in homework 2. I don't want to muddy the waters.
They were speaking a lot about like how to do acquire and release, and at the end they are like, oh, but actually you can just use reads.
Always use with. Yeah. Always just use with. We're not gonna. You won't be able to in OpenMP without. We could add some structures there. The with syntax is a lot easier and guarantees that even if your thread crashes, maybe not if it crashes, but almost always if it errors out or something, other threads will continue. The with syntax is much cleaner. And a lot of languages support something like that. Other questions about Python threads or OpenMP threads?
You have one core that worth like threading OpenMP?
If you have one core, is it worth threading? Yes, usually. Well, so I answered this on Piazza in a little, but if you have one core, if you have a one-core machine, but it has multi-threading, then it might look like multiple cores, or if it has this hyper-threading where you can interleave 2 threads of computation very close, then yes, definitely. In fact, if you don't thread, you won't get full performance that you could, right? Because there's a lot of compute logic on the core that won't be used if you're multiplying down one. If one thread is multiplying, the other one can be adding, for example. If you've got I/O-bound tasks thread, right? Some of them are going to be waiting on disk or network or something like this. Other ones can be computing. So definitely thread then. You can increase, in fact, if it's I/O bound, lots of threads. A thread per event going on can be quite useful. You do have to be careful in sort of cluster situations. I asked for one core, and if I run multiple threads, if it's 2, fine. If it's 8, then I might get a call from research computing staff saying, you're gaming the system. But in general, a couple threads can be quite useful. And if you don't have a lot of scheduling overhead, it won't cost, right? You'll do a big block of, the worst case, well, if you don't have a lot of scheduling overhead, then nothing goes wrong. If your scheduling overhead is 0, you'll do a big block of computation, you'll do a different block of computation in another thread, but you get the same work out. If the scheduling overhead gets too high, then it starts to cost. But 2 threads, 3 threads, 4 threads is probably fine. There was a question that someone asked, why do we need 2 locks here, right? We grab the GIL, which is we grab a lock in OpenMP, and then we grab the GIL, which is another lock. Why not just grab the GIL? The GIL is not the same as other locks. Do people understand why? When I grab the GIL, do I have the GIL? Do I never give up the GIL? No, I don't always have the GIL, is the answer. The GIL is the global interpreter lock, but as I do interpreting, so it allows me to do things like high-level things like string formatting or calling print or any other Python function. But the GIL has this timer or an instruction counter. So basically my thread executes for a while, but anywhere in there, it might have to give up the GIL. And that's just part of the interpreter. The interpreter says, oh, your turn is done. Someone else gets it. So if I didn't have these outer locks, these OpenMP locks, I might run through part of the print. I might format the string and get ready to print it, and then give up the GIL. And someone else could come in and print. And in fact, this is just the example from the 1 lecture ago. If you take out the OpenMP locking, just comment those out and run it, you will see that lines start to run over each other, that it doesn't print as cleanly as when you have them in. And that's what's happening is the GIL, all the threads are hitting that with GIL statement basically at the same time, right? I've got 100 threads. They all hit the with GIL. One of them gets to go forward. It goes forward, it starts to print, it prints, it comes back. Another one gets the GIL. But some of them get the GIL, start to print, get suspended, and someone else gets to enter the GIL section. And then they print, and then the other one finishes its print, and then it's garbage. Because the GIL is not a lock that you just hold, you're guaranteed to have the GIL anytime anything is actually happening in your thread, but it doesn't say, I get the GIL and no one else can have it. So that's just important to understand why we need 2 locks and why they're different. Well, so you'll want to be able to use this structure for debugging in particular. For homework 2, when you're creating parallel ranges with no GIL and it's running and you've got a bug, be willing to drop this in there, but understand that if you want to do some actual debugging in there, you may need to lock another way to make sure that it's only one thread running. Well, you need the GIL, at that point you need the GIL just to go back into the interpreter. So you need the outer lock to protect, basically to protect standard out. You need the inner lock to be able to call print, because print's a Python function. Also to call format, also to construct a string. All right, so you need the GIL for 2 purposes. One is partly it protects Python's internal structures. Partly it allows you to do things in Python when you're inside a no GIL section. Oh, yeah, it's with no GIL, right? So it's Python multi-threading support. So the question is what causes this suspend to happen? Python multi-threading, the model is, there are 2 models actually, and I forget which one is newer. One of them exists in 2.6, one of them exists in 2.7. It's either timer-based or instruction count-based. What happens is you get a certain time, each thread, assuming I'm running multiple threads in Python land, so Python threads, and everything's interpreted. And we've seen these diagrams where we have one thread runs, and then it suspends and another thread runs, right? That suspend is caused by reaching a counter or reaching a certain timer. So I think it used to be 500 ticks, which is 500 instructions of the interpreted code. So it would run until that 500 boundary and then give up the GIL and some other thread would run. And now I think it's more timer-based to be more fair. But it can happen, it doesn't happen between lines of Python. It happens within the bytecode interpreter that Python goes to, which each line may be multiple statements. And it can suspend at any one of those statements, basically. Okay, so you may think it's a small piece of code that no suspend could happen in there, but it's not true. Almost anywhere a suspend can happen. And you see it in this example. If you run this, you will see some of them will print part of their line, and then before they can print the return, at the end, another line prints, and then later on they come back and print their return. Okay. If you add a few more extra prints in here, in fact, if you make 3 of these with separate numbers, you'll see it even more. It'll be obvious that threads are suspending within the GIL block. But only if you remove the OpenMP threads. Okay. That's an implementation detail. I mean, it happens in any interpreted language, especially if it's multi-threaded, but important to know. Okay. Other questions about this sort of locking or the GIL? All right, next time, we're going to talk about instruction level parallelism. Basically, MMX, SOC, AVX, these are all just names for do something with multiple pieces of data per compiler instruction, per low-level instruction, and how to use them.
I didn't get it. You updated the run.
Let's wait until, yeah. So let's talk about this just after. All right, see you Friday. Are there more questions before? No? Everyone wants to leave? Okay.